Welcome to the seventh and final thermal physics lecture. In this lecture we're going to look at energy transfer mechanisms, specifically ways of transferring heat from one body to another. This lecture is going to look at sections 18.6 of your textbook. First of all, a quick recap of the most important ideas from last lecture. Last lecture you saw this equation for the mean free path. So the mean free path is the distance on average that a gas molecule can travel without colliding with another gas molecule. So lambda, the mean free path, is given by 1 over the square root of 2 pi d squared, where d is the diameter of the molecule, times n on v. So n is the number of molecules in our sample and v is the volume of the sample. So n on v is the density of the gas molecules. After that, we had a look at Maxwell's speed distribution law. So this gives a nice curve like this, showing the different velocities of the particles making up the gas. So the gas does have an average velocity, but some of the particles have a velocity greater or less than this average velocity. So we saw that the probability of a particle having a particular speed v is given by 4 pi m, where this is the molar mass in kilograms per mole, over 2 pi RT to the 3 on 2 v squared, where v is the velocity, e to the minus mv squared over 2 RT. So we could use this and integrate it to end up with our root mean squared velocity as well as our average velocity, and we could also use it to work out the most probable velocity for a molecule to have. After that, we had a look at specific heat. We said that specific heat is the amount of energy, usually in the form of heat, that needs to be added to raise 1 kilogram of a substance 1 degree C or 1 Kelvin. So Q, the amount of heat added, is equal to M, the mass of our substance, times C, the specific heat of the substance, which is different for different substances, times the change in temperature. We also considered phase transitions. So when a substance undergoes a phase change, this requires energy, and the amount of energy required is equal to the change in mass. So this is the change in mass of the substance at one particular phase. The overall mass is not changing, it's just if you're melting ice, for example, the mass of the ice does change as the ice becomes water, times L, which is the latent heat, which you will be given. You can look it up in a table. Now there's 3 main methods for transferring heat from one body to another. We've got conduction, we've got convection, and we've got radiation. And in this lecture we're going to be looking at these in a bit more detail. Okay, now as you are probably aware, metal is a very good conductor of heat. If you touch something cold, a cold piece of metal, then it feels very cold as it's transferring heat away from your fingers. Asbestos, on the other hand, was such a popular building material because it's a very poor conductor of heat. So it's a very good insulator for houses and things. Let's have a think about how heat flow would work. Well, the amount of heat transfer is going to be a power because it's the energy transferred per unit time. So we can write P is equal to Q, the heat transferred, over delta T, where this is the time. Now, if we consider having a slab of a substance, if it has a very large surface area, we'd expect more heat to be transferred. So we've got that it's proportional to the surface area. If there's a very big temperature gradient between the two sides of the surface, then we would expect the heat to flow more quickly as well. So it's proportional to the change in temperature, the temperature difference between the hot side and the cold side. Now if we have a very thick piece of material, we would expect heat to flow more slowly. So the amount of heat transfer is actually inversely proportional to the width of the substance. Okay, so we've got a proportionality. This proportionality constant, we give the symbol K. This is the thermal conductivity, and it's different for different materials, as some materials are good conductors of heat, others are bad conductors of heat. We have an absolute value sign here. We can consider the power transferred to be positive, but it's always going to flow from the hot side to the cold side. So this table presents thermal conductivities for some common substances. For metals, you can see they're relatively high, aluminium 238, copper 397. For most other materials, they're much lower. So asbestos 0.08, that's a very good insulator. Rubber 0.2, water is 0.6. Okay, diamond is an exception. It's an exceptionally good conductor of heat. Its conductivity constant is 2300. Gases are generally very poor conductors of heat. There's a lot of space between them, so they cannot conduct heat quickly. So air has a thermal conductivity of about 0.0234. Okay, let's have a look at this problem. We've got a rod, we've got a hot side and a cold side, and we'll ask what is the rate of energy transfer in this case. Okay, in this case, we've got P is equal to Ka dt dx is our formula. Let's ignore the absolute value signs for now. So we can write this as P dx is equal to Ka dt. To work out this, we can integrate. Now x, if this is at x equals 0, then this end is at x equals L. So we're integrating from 0 to L. And the temperature at this end, we've got TH, and at the other end, TC. So integrating, we've got P, L minus 0 is equal to Ka TC minus TH. So we can write the power transferred is equal to Ka. Now remember this absolute value sign, this Tc minus Th, this is the cold temperature minus the hot temperature, that's going to be negative, so we need to make it positive, so Th minus Tc over L. So this is possibly a more useful form of this equation here. This is the one given on your formula sheet. This is probably a more useful form of it. Okay, another example. A bar of gold is in thermal contact with a bar of silver and the same length and area. One end of the compound bar is maintained at 80 degrees C and the opposite end is at 30 degrees C. When the energy transfer reaches steady state, what is the temperature at the junction? Okay, let's sketch the diagram for this problem. We've got a hot end at 80 degrees C. We've got a cold end down here at 30 degrees C. We've got metal bar. This part up the top is formed of gold. This part down the bottom is formed of silver. We're asked what's the temperature here at the junction between them. And we can look up in our table and see that the thermal conductivity of gold is 314 watts per meter per degree C. And that the thermal conductivity for silver is 427 watts per meter per degree C. Now, the most important point for answering this question is that it says it ends up reaching thermal equilibrium. So that tells us that the power transferred through the gold must be the same as the power transferred through the silver. If this was not the same, it would suggest that somewhere in the middle we're either having the energy collecting or the energy being depleted, which would mean that it would get very hot or very cold in the middle here, and that's not what happens as it reaches thermal equilibrium. So we know that the power flow through the gold is equal to the power flow through the silver. Now all we need to do is substitute into our equations. So we've got P is equal to Ka, change in temperature over the, well, in this case the length. We can say that these have length L if we want. They have the same length. Okay, so for gold, we've got K for gold times the surface area of the gold times the change in temperature. So this ends at 80 degrees C. This ends at Tj. And then over the length, and that's the same for the silver, Kag, A. And now the hot end is at temperature Tj, the junction temperature, and the cold end's at 30 degrees C. And that is over L. So the L's and the A's will cancel out as they're common factors. So we can put all the TJ's onto the left-hand side and all the numbers on the right-hand side. Okay, so let's substitute in. we've got 314 TJ. And then over this side, let's move this over. So plus 427 TJ is equal to 314 times 80 plus 427 times 30. Okay, so now we can just solve for TJ. 314 times 80 plus 427 times 30 over 314 plus 427. Solving that on the calculator, we end up with 51.2 degrees C. Okay, now this is not something that you're going to be examined on in the physics course, but it is important for engineers to understand because this is how this theorem is applied to engineering. So often when you buy a material to build something from, it's got an R value marked. R is equal to our length term divided by our conductivity term, and it's referred to as an R value. So the formula for the rate of flow is heat with R values is P is equal to the surface area, the hot side, the difference in temperature between the hot side and the cold side, over the sum of the R values for whatever materials you're building it from. So this just says that if you have a composite material, to get the total R value, you just need to add the R values from each part. This table presents the R values for some substances that are commonly used in building. This table is actually taken from the textbook, which is an American textbook, and so it has very strange units. You can see the units for R values here are feet squared per degrees Fahrenheit per hour per British thermal unit. So in our more normal units, the feet squared becomes meters squared, degrees Fahrenheit becomes degrees Celsius, and this is time divided by energy units. British thermal units are related to joules. To get from one to the other, you need to multiply by 1055. But the time divided by the energy is equal to the inverse of watts. So we have per watt here instead of HBTU normally. To get from these very weird American units to our units, you just divide by a number which is approximately 6. These are just presented here so that if you ever see these units, you know what it's talking about. But in physics, we will not be using these units, we will be using SI units. So here's a question for us to try. Calculate the total R value for a wall constructed as shown. So we've got bricks, we've then got some sheathing, we've got an airspace, and finally we've got some plasterboard. Okay, so let's just draw a little diagram. We've got bricks here, and there's 10 centimeters of bricks. We've then got 1.2 centimeters of sheathing. We've got 2 centimeters of air and 1.2 centimeters of plasterboard. And we know that P is equal to A dH minus TC over the sums of the R values, and this is equal to Ka delta T over L, and so we know that the sums of the R's is equal to L on K. And so all we need to do is add the L on K for each of these different materials. So we'll need to look that up in the table. K for brick is equal to 0.70 watts per meter per Kelvin. K for sheathing is equal to 2.0 watts per meter per Kelvin. K for air is equal to 0.0234 watts per meter per Kelvin. And finally we've got plasterboard, so K for plasterboard is equal to 0.174 watts per meter per Kelvin. So R is equal to 0.10 meters over 0.70 plus we've got the sheathing, so that's 0.012 meters over 2.0 plus the air, which is the 0.02 over the 0.0234 plus the plasterboard, which is the 0.012 over 0.174. So solving this on the calculator, we end up with 1.073 meters squared kelvins per watt. And so that's the R value for this wall. Okay, another heat flow mechanism is convection. Now the formulas governing convection are very complicated and beyond the scope of this course, but you need to just be aware that convection occurs. How it happens is, imagine this radiator down here. Now that's heating the air around it. As we heat air, it becomes less dense and expands. If the air is less dense than the surrounding cold air, then it will float to the top. So in a house here, you've got the hot air floating to the top. It then hits the roof where it's reflected off and you get these convection currents generated. As it is in thermal contact with the surrounding air, as it undergoes this path, it will lose some energy, and so it will become cold again by the time it gets back to the radiator. So we get convection currents formed this way. Another heat flow mechanism is through radiation. All objects radiate energy, and the amount of energy they radiate, so P is Q over T, is given by sigma A E T to the 4. P is in watts in this case. Sigma is a constant called Stefan's constant, so its value is here. A is the surface area of the body. E is an emissivity constant, which is different for different substances and is between 0 and 1. It refers to how well a body will absorb all the radiation that falls on it. A black body will perfectly absorb all radiation that falls on it, so it has an emissivity of 1. A mirror, which reflects almost all the energy which falls on it, has an emissivity much closer to 0. And then we've got our temperature in kelvins to the power of 4 here. It's very important that you do convert temperature to kelvins when using this, as it's not a change in temperature, it's an actual temperature. Now what's more interesting than just the amount of heat that a body is emitting is the net heat flow, because as a body sitting in its environment, it's absorbing energy from the surrounding environment as well as radiating it. So what we're interested in really is the change in energy of that body, so the net transfer of heat. So this is given by sigma A E T to the 4. This is the temperature of the body, and this is the temperature of the surroundings. You're best off when you're answering questions like this to state whether this is a net flow into or out of the body. So if a body's hotter than its surroundings, it's going to be losing energy to its surroundings. If it's cooler than its surroundings, it's going to be absorbing energy from its surroundings. So questions that you can do to practice using this formula are homework set 5 for 1121 students, questions 3, 4, 5 and 6. For 1131 students, questions 4, 5, 6 and 7. Let's do a few examples now. A sphere of radius 0.5 meters, temperature 27 degrees C and emissivity 0.850 is located in an environment of temperature 77 degrees C. At what rate does the sphere A emit and B absorb thermal radiation? And C, what is the sphere's net rate of energy exchange? Okay, so for this question, we're going to assume that radiation dominates. We're not told anything about the conductivity of the environment, so let's just assume it's very low. Okay, so let's draw a diagram for this one. We've got a sphere. The sphere is at 27 degrees C, and the surrounds are at 77 degrees C. The surface area of the sphere is given by 4 pi r squared, so that's 4 pi times 0.5 squared. These will cancel, and so the surface area is pi. Okay, so part A asks us what's the rate of energy emission. So the power emitted is equal to sigma A E T to the 4. So this is sigma is 5.6696 times 10 to the minus 8 times the surface area times the emissivity, which we're told was 0.85, times the temperature to the power of 4. So that's 27 plus 273, or to the power of 4. Solving that on the calculator, we get 1,226, which is 1,230 watts, just the 3 significant figures. Okay, part B, we were asked what was the rate of energy absorption. So this is equal to sigma A E T naught to the 4, so the temperature of the surrounds to the power of 4. So same numbers, 5.6696 times 10 to the minus 8 times the surface area times 0.85 times, in this case, 77 plus 273 to the power of 4. Solving that on the calculator, we end up with 272. So, sorry, 2,272. So 2,270 watts. Okay, finally, we're asked for what is the total energy transfer. So P total, you can see it's absorbing more than it's emitting, but we just do the difference between these two. So that is equal to 1,040 watts. Next, a solid cylinder of radius R1, 2.5 centimeters, length 5 centimeters, and emissivity 0.85, and temperature 30 degrees C, is suspended in an environment of temperature 50 degrees C. What is the cylinder's net thermal radiation transfer rate, P1? And B, if the cylinder is stretched until its radius becomes 0.5 centimeters, its net thermal radiation transfer rate becomes P2. What is the ratio of P2 on P1? Okay, so in this question, we had a cylinder. The radius of the cylinder, R1, is equal to 2.5 centimeters. The height of the cylinder, H1, is equal to 5.0 centimeters. The emissivity is equal to 0.85. The temperature of this cylinder is 30 degrees C. And the temperature of the surroundings is equal to 50 degrees C. In part A of the question, we were asked to calculate the net energy transfer by heat from this cylinder. Okay, so this cylinder is going to be gaining energy as it's got a lower temperature than its surroundings. Okay, so the formula we'll need to use is sigma A E T to the 4 minus T naught to the 4. So we need to work out A, the surface area. This is a cylinder, so it's got two circular ends with the surface area pi r squared, and then it's got this rectangular piece here, which is the circumference of a circle times h. Okay, so substituting in, we've got 2 pi times 0.025 squared plus 2 pi times 0.025 times 0.05. Solving that on the calculator, you end up with 0.01178 meters squared as the surface area. Okay, now we can substitute everything in here. Sigma, Stefan's constant, 5.6696 times 10 to the minus 8 times the surface area we've calculated down here, 0.01178 times the emissivity, 0.85 times T to the 4. So that's the 30 plus 273 to the 4 minus the temperature of the surroundings, so 50 plus 273 to the 4. Solving that on the calculator, we end up with minus 1.39 watts. So this minus is just because T to the 4 is lower than T naught to the 4. So we should put 1.39 watts transferred to the cylinder. Okay, part B. In part B, we're stretching out this cylinder so that it's got a new radius of 0.5 centimeters. We're keeping everything else the same,
So we're keeping the volume of the cylinders the same because we're not creating or destroying matter. So volume 1 is equal to volume 2. The volume of cylinder 1 is pi r1 squared h, and the h1, and the volume of cylinder 2 is pi r2 squared h2. So we've been told r2. What we need to work out to get the surface area of our second cylinder is the length of the cylinder. So h2 is equal to r1 squared h1 over r2 squared. So that's 2.5 squared times 5 over 0.5 squared. That gives us, when we solve it on a calculator, 125 centimetres. Okay, so A2, we can just substitute into this formula, 2 pi r2 squared, so 2 pi times 0.005 squared plus 2 pi times 0.005 times this new length, 1.25. Solving that on the calculator, we end up with the new surface area of 0.0394 meters squared. We're asked to find the ratio of energy transfers, so P2 over P1. This is sigma A to E t to the 4 minus t naught to the 4, sigma A1 E t to the 4 minus t naught to the 4. Everything apart from the surface area is staying the same, so it will cancel out. So we've just got A2 on A1. A2 is 0.0394 over 0.01178, that's our A1. And so solving that, we end up with 3.34. So cylinder 2, the long skinny one, loses heat about 3.34 times as quickly as cylinder 1, the short stubby one. Next question. 2 light bulbs have cylindrical filaments much greater in length than in diameter. The evacuated bulbs are identical except that one operates at a filament temperature of 2100 degrees C and the other operates at 2000 degrees C. A. Find the ratio of the powers emitted by the hotter light bulb to that emitted by the colder light bulb. And then B. With the bulbs operating at the same respective temperatures, the cooler light bulb is outed by making its filament thicker so that it emits the same power as the hotter one. By what factor should the radius of the filament be increased? Okay, so we've got filaments which are long tubes. So the surface area, we can neglect these circular bits at the end because they're so small compared to the rest. So the surface area is given by 2 pi r times the length. So just the circumference times however long this filament is. Okay, now in part A, we were asked to calculate the power emitted by the hotter one compared to the power emitted by the colder one. Okay, so let's substitute in everything we know. We've got sigma A E, and now the hotter temperature, TH, was 2100 degrees C, and the cold temperature was 2000 degrees C. That's what we were told in the question. So this is 2100 plus 273, all to the power of 4, over sigma A E 2000 plus 273, all to the power of 4. These are all common factors, so they cancel out. So solving this on the calculator, we end up with 1.19. So the hotter one emits 1.1 times as much power as the colder one. Now in part B, we were told we want to keep the temperatures the same and change R. Okay, so now we want pH over PC, that we want them to emit the same amount of power. So we want this to be equal to 1. So this is equal to sigma A of the hot one, E, and this temperature hasn't changed, so it's 2100 plus 273 to the 4, over sigma, the surface area of the cold one. That's 2000. Okay, so that cancels, that cancels. Now this part we've solved up here. We know that the value of this is 1.19, so let's replace that with 1.19. And now we've got 1 over 1.19 is equal to AH over AC, and we've seen that the surface area is equal to 2 pi, now this is R for the hot one, times the length, over 2 pi R for the cold one times the length. Now the lengths we're saying are the same, these 2 pi's are also the same. So we've got 1 over 1.19 is equal to the radius of the hot one over the radius of the cold one. Okay, so this tells us that the radius for the cold filament needs to be 1.19 times the radius for the hot one. So by a factor of 1.19. Next question. A copper rod, an aluminium rod, and a brass rod with K is equal to 109 watts per meter per Kelvin are each 6 meters long and are placed end to end with the aluminium rod between the other two. The free end of the copper rod is maintained at water's boiling point, and the free end of the brass rod is maintained at water's freezing point. What is the steady state temperature of A, the copper aluminium junction, and B, the aluminium brass junction? Okay, let's start by drawing our diagram. We've got a metal rod with 3 different types of metal. Here's our copper. The thermal conductivity of copper is given by 397 watts per meter per Kelvin. We've got aluminium in the middle. K for aluminium is equal to 238 watts per meter per Kelvin. And then we've got brass on the end. The thermal conductivity of brass is equal to 109 watts per meter per Kelvin. This end is the hot end, it's at 100 degrees C. This end's the cold end, it's at 0 degrees C. Let's call this temperature of junction 1, TJ1, and this one temperature of junction 2, TJ2. Okay, so part A is asking us to find TJ1, part B is asking us to find TJ2. Now what we know is that this reaches a steady state, which means that we must have the same amount of heat flow through this part as through this part and through this part. If this wasn't so, we'd have a build-up of energy at one place, and so we would not reach a steady state. Okay, so that tells us that P, which is equal to K for copper. Now, for copper, it's got surface area A, and it's over a length L, which is 6 meters in this case, and the temperature change across the copper is 100 minus TJ1. This is equal to the heat flow, let's put it up here, this is equal to the heat flow through the aluminium. And the hot side is TJ1, the cold side is TJ2, and then this is also equal to the heat flow through the brass. The hot side is TJ2 and the cold side is 0. Okay, now let's cancel out our common factors. So get rid of the P now. Cancel out the A's and the L's in each case. So we've got K for copper, 100 minus TJ1 is equal to K for aluminium, TJ1 minus TJ2 is equal to K for brass times TJ2. Now we've got 3 equations and 2 unknowns here, so we need to solve it simultaneously. We can write that TJ2 using this part and this part is equal to K for copper, 100 minus TJ1 over K for brass. So if we wanted to put in numbers, K for copper is 397. So this is 397 over 109, 100 minus TJ1. Okay, now what we can do is use this part and this part. Let's call this 1, 2. Use 1 and 2, and we can substitute in this for our TJ2. So we've got copper, that's 397, 100 minus TJ1 is equal to aluminium, which is our 238, TJ1 minus TJ2, which is 397 over 109 times 100 minus TJ1. Okay, now we've only got one unknown, so we can collect together all the TJ1s over this side and all the pure numbers over this side. So we've got 397 times 100 plus 238 times 397 times 100 over 109. So that works out to 126,384. Let's pull TJ1 out as a common factor, and then we've got this 238. We've got the 397 over 109 times the 238 for this TJ1, and then we've got this TJ1 here, which is 397. So solving, we can divide this through by this, and we end up with TJ1 is equal to 84.2 degrees C. Okay, so this is our answer for A. For part B, we need to find the temperature of junction 2. So TJ2 is equal to, we said up here it was 397 over 109, 100 minus TJ1, which is 84.2. So solving that, we end up with 57.5 degrees C. Okay, so both of these temperatures are between 100 and 0 degrees C, as we'd expect. So this seems like a reasonable answer. Final question. Suppose that you intercept 5 times 10 to the minus 3 of the energy emitted by a hot sphere of radius 0.02 meters and emissivity of 0.80. The surface temperature is 500 kelvins. How much energy do you intercept in 2 minutes? Okay, so in this one we have a sphere. Its radius is equal to 0.02 meters. So its surface area is 4 pi r squared. Substituting this in and solving it on the calculator, we end up with 5.03 times 10 to the minus 3. So the power emitted by this sphere is given by sigma A e t to the 4. Substituting in 5.669 times 10 to the minus 8 times our area, 5.03 times 10 to the minus 3, it's meters squared, times E, which we're told is 0.80, times the temperature to the power of 4, which is, we're told, 500 kelvins. So solving that, we get 14.2 watts. So this is emitting 14.2 joules each second. That's what a watt is. So now the energy we intercept, energy is equal to power times time, and we're only intercepting part of the energy, 5 times 10 to the minus 3 of the energy. So we times this by the 14.2, the rate of energy emitted, and then we need to times it by the time. It's 2 minutes, so 2 times 60. So that gives us 8.5 joules is intercepted. That's the answer to this question, and that's the end of this lecture.